I'll be turning to Kaitlyn Kalua. She is the Deputy Director for the California Ocean Protection Council, a cabinet-level state policy body that works to ensure healthy coastal and ocean ecosystems by advancing innovative science-based policy and management, making strategic investments, and catalyzing action through partnerships and collaboration. Kaitlyn is responsible for the development and implementation of policies and programs to advance the Ocean Protection Council's strategic priorities across climate, biodiversity, equity, and a sustainable blue economy. She received her JD in Environmental and Public Law certificates from the University of California, Davis School of Law. Kaitlyn.
Here we go. Thank you. That was my test. Well, perfect. I'll stay on this introductory slide just for a moment. So as we know, the world's coast and ocean are significantly affected by climate change. They absorb carbon emissions, which scientists have then observed biological, chemical, and physical changes that include sea level rise, increased severe storm events, ocean acidification, warming seas, and shifting species distributions. Such impacts currently and will continue to threaten California's communities and ecosystems for decades to come. Next slide, please. Tracking key climate change impacts to our coast and ocean is critically important to inform our actions and decisions, and this includes impacts to our wildlife, communities, as well as economy. Today, I will focus on a relatively small suite of ocean and coastal indicators, which only begin to scratch the surface, but also provide insight into the way climate change and related stressors are connected and compound the challenges facing the health of our coast and ocean. Next slide, please. Sea level rise has significant impacts on coastal communities and ecosystems, leading to coastal erosion, increased flooding, thank you, Michael, intrusion of saltwater into freshwater aquifers, as well as loss of habitat for plants and animals and recreational space and access for people. Informed by tide gauge data over the past century, sea levels across the California coast have risen approximately 6 inches with an average statewide increase of 0.9 inches per decade, which is consistent with global patterns of sea level rise. However, this rate is projected to significantly accelerate. OPC recently released, just this past Friday, its draft 2024 update to the state of California's sea level rise guidance. This guidance is updated approximately every 5 years to incorporate the latest science as well as updated projections for sea level rise through 2150. So key takeaways are provided here on this slide, and that the latest projections provide that the average base sea levels are anticipated to increase by just under a foot, 0.8 feet, to 1.2 feet statewide through 2050. So it did narrow that range of anticipated projections in the near term. That is only three decades, 30 years, as well as a 3.1 foot to 6.6 foot increase through 2100 under 5 different scenarios that are based on greenhouse gas emissions, rate of sea ice melt, along other factors. However, there is local variation. Vertical land motion is a primary driver of local variation in sea level rise across the state. For example, in Humboldt Bay, and this is where this graphic comes into play, paying attention to the top 2 northmost arrows. Right now I'm focusing on that large, or not really large, but small, deep red one. In Humboldt Bay, land is sinking at among the highest rates across the state, and by consequence, sea level rise is projected to range between up to 1.63 feet in the next 30 years, which is an increase of the high scenario projection of 1.2 feet by 2050 statewide. Meanwhile, also shown in this figure, the arrow right above, the trend of relative sea level rise is increasing at nearly all outer coast tide gauges in California, except in Crescent City. That again, that's that northernmost figure. In Crescent City, land uplift due to vertical land motion is surpassing the current observed rate of sea level rise. Next slide. The predominant impacts of sea level rise for California are flooding and erosion, and as sea levels rise, we can expect coastal flooding to occur more frequently, to last longer, and to extend further inland, damaging California's roads, property, and infrastructure. The potential loss or damage to public infrastructure, health and safety, and natural habitats due to sea level rise is significant, and it is urgent. Approximately 700,000 residents and $200 billion in property across California could be exposed to a combination of storms and sea level rise-driven flooding during the century. Recent king tide events, those extreme high tides, occur several times per year and have recently co-occurred with winter storms, causing significant damage and cost across the state. The financial toll of last year's storms, this is not including this past December or even this past month of January, exceeded $34 billion in damage statewide. Importantly, the catastrophic flooding in 2022 to 2023 is a stark indicator of the future challenges and impacts we can expect to see from sea level rise and climate change, and that these adverse impacts are not distributed equitably. Sea level rise hazards will disproportionately impact communities that have the least capacity to adapt and may exacerbate existing environmental injustices, particularly those in those low-lying areas or located near contaminated sites with contaminants that can mobilize through flooding. Lastly, communities across the state do have difficult choices to make that will impact irreplaceable biodiversity and the safety of communities. We must plan proactively. Because if we don't plan and manage with intent and react only to piecemeal emergencies, these inequities and biodiversity losses will be exacerbated. Next slide, please. As greenhouse gas emissions increase, this results in an increase in carbon dioxide absorbed by the ocean, which in turn lowers pH and causes ocean acidification. Long-term data is limited statewide, and the best available data currently is in Southern California, which is demonstrated in this graph. I do apologize if it's coming out a little gritty. The graph here is, again, limited to Southern California waters, but demonstrates that these coastal waters are acidifying. Here, subsurface waters at 100 meters in depth are trending towards, and already often below, critical thresholds where shells would be exhibited to moderate severe shell dissolution, that is, for calcifying marine organisms. Again, a little difficult to see, but those critical thresholds are shown in that red horizontal line, as well as a intermediate threat at that. I'll go in the next slide to describe exactly what these threats are. There's a dotted line as well as that severe dissolution threshold demonstrated on this graph. Next slide, please. So as I was fumbling through those red lines, essentially we evaluate the impacts of ocean acidification based on the critical threshold of aragonite saturation state. That's the baseline ability for calcifying organisms to maintain and build their shells as well as their exoskeletons. This is a state of 1.4 when sensitive organisms display that moderate dissolution. That's that middle image there, as well as a state of 1 where dissolution becomes severe. That's that far right-hand side image. OPC has invested in expanding California's acidification monitoring programs in 2 ways. The first is geographical, to increase data in Central and Northern California, as well as a biological component to our 2 future monitoring programs to assess to the extent to which biota are affected by acidification. This includes a focused assessment of crabs and snails and other known as pteropods, other marine organisms that form the base of our marine food web. Next slide, please. Ocean acidification, which results in lower pH, is a newer phenomenon, but often co-occurs with hypoxia, that is low dissolved oxygen, due to elevated water temperatures as well as accelerated nutrient delivery loads from land. Ocean acidification and hypoxia can affect organism survival and growth, and these effects vary among species and in life stages, and often depend on whether hypoxia or low pH occur in tandem or alone. In California, the California Cooperative Oceanic Fisheries Investigation, that is CalCOFFI, has been taking measurements of dissolved oxygen periodically off the coast of Southern California, that is San Diego to Point Conception, since 1950, and more consistently since 1984, which provides the state with its most consistent data set for dissolved oxygen. Again, demonstrating a severe data limitation for the state of California in that we really only have consistent rich data for the Southern California region and less data available in Central and Northern California. Changing ocean chemistry in concert with changes in temperature may lead to even greater and more diverse impacts on coastal marine ecosystems. And a current inquiry that OPC is investigating is that connection between ocean acidification, hypoxia, and potential habitat compression. That is the vertical compression of viable habitat for calcifiers and marine species within the water column. Next slide, please. Ocean warming is a critical climate change indicator, which again reflects that absorption of excess heat from the oceans due to increasing greenhouse gas concentrations and emissions. Warming ocean temperatures can influence weather patterns, causing more intense extreme weather events, and have profound effects on California's marine ecosystems, driving species shifts, oxygen depletion, again, hypoxia, leading to mass strandings of marine mammals and seabirds, toxic algal blooms that can affect commercial and recreational fisheries, as well as a rapid loss of kelp forests, which we'll explore very momentarily. This figure demonstrates anomalies in sea surface temperature for July of 2010, 2015, 2020, and 2023. which generally July is a period of upwelling along the California coast, in which historically results in cooler sea surface temperature, which again demonstrates these anomalies. Next slide, please. Now looking only at 2023 data, in mid-May of 2023, a marine heat wave formed off California's coast that was the fourth largest by area and ranks among the top 20 by duration, according to NOAA data. In late October of this year, a secondary marine heat wave also formed off the northwestern coast of California. Next slide, please. Which has impacts to habitats such as kelp. This is a figure demonstrating kelp canopy cover over a period of about 20 years, northern central and southern California. And kelp forests are fundamental to California's marine biodiversity and ocean economy. Kelp forests also naturally fluctuate from year to year. Satellite imagery dating back to 1984 shows also significant potential natural interannual variability, which does again make that difficult to make that connection between what is natural background variability versus what is being is actually connected then to climate change and human-induced stressors. You'll see here on the north coast, that is the California-Oregon border down to San Francisco Bay, more than 95% of bull kelp canopy was lost after an extreme marine heat wave that took place between 2014 and 2016. With it brought a perfect storm of additional changing ocean conditions. Some here in the room may be familiar with the decimation of sea stars due to sea star wasting syndrome and an explosion of kelp-eating purple urchin populations in the north coast of California. Recovery has been limited, and in 2023, total kelp canopy coverage remains at less than 10% of its historical average. That's based on 2023 data. Kelp may be increasingly vulnerable as climate change accelerates, and to address this catastrophic loss, we're continuing to invest in research, restoration, and partnerships with communities and tribes along the California coast. Next slide, please. Meanwhile, harmful algal blooms pose a threat to California aquatic ecosystems. These HABs can be formed by numerous phytoplankton and cyanobacteria species that produce toxins. And again, there's that high variability between both HAB species, but also the seasonality statewide. And that's what these two graphs are meant to indicate, is that seasonal sub-region variability, and that blooms of Pseudonychia have exhibited that exact strong seasonality, as well as that sub-regional variability. These figures show the relative abundance of Pseudonychia seriata, that's in blue, and then the domoic acid that is produced by these HAB balloons. Those occurrences are demonstrated in these orange bars at two central coast locations that demonstrate again that seasonality and sub-regional variation. Pseudonychia habitat is also migrating northward, and a new sustained domoic acid hotspot has emerged following the 2014 to 2016 marine heat wave. Next slide, please. Domoic acid produced by Pseudonychia has serious effects on marine life as it bioaccumulates and impacts the full marine food web. It can cause marine mammal strandings events as well as mortality. And this past year, there were two significant marine mammal stranding events that included sea lions and dolphins, primarily in Southern California, but also across the state. The first occurred in August to October of 2022, which was centered in the Santa Barbara Channel, and linked to over 300 marine mammal strandings that stretch from Los Angeles to San Mateo. The following summer, this past summer, May through July of 2023, an even larger mass stranding event occurred that impacted approximately 1,000 marine mammals, with animals stranded throughout Southern California. Impacts of HABs also include lower dissolved oxygen, hypoxia from algal decay that causes significant fish kills, such as the red tide event that was seen in the summer of 2022 in San Francisco Bay that resulted in the death of tens of thousands of fish due to lower dissolved oxygen, and economic impacts due to fishery delays and closures. Next slide, please. California has faced significant fisheries closures and delays this past year connected to the impacts of climate change. HAB toxins, such as domoic acid, impair recreational and commercial shell fisheries, including Dungeness crab. And the Dungeness crab season in California has experienced multiple delayed openings as well as early closures in recent years. In addition to domoic acid events, with increased temperatures offshore, whales have migrated closer inshore, staying longer as prey availability has also shifted with changing ocean temperatures. This has resulted in increased entanglements as whales stay longer in these near shore areas where crab pots occur for recreational and commercial Dungeness crab fishing, which has led then to these delayed openings and early closures. Climate change impacts on land have also impacted salmon fisheries. Drought and wildfire impacts have impacted spawning salmonid habitat, which resulted in low population abundance forecasts that caused closure of commercial and recreational salmon fisheries this year. And consequently, this was the first and unprecedented year that the Yurok Salmon Festival was also without salmon. Next slide, please. Although there is hope, California is home to the largest marine protected area network in the nation, and it's an important marine ecosystem conservation tool as well as a global model for marine conservation worldwide. This is a network of 124 areas that span the coastline and include a wide diversity of habitats. In January of this year, the state released its first ever decadal management review. So again, this is a long-term data set that overall found that MPAs are increasing marine life and generating ecosystem benefits for California's coast and ocean. Fish are generally bigger and more abundant, as well as have shown a higher degree of climate resilience, or at least potential climate resilience, as fish in other species populations and some MPAs did rebound faster after the marine heat wave event of 2014 to 2016. Next slide, please. I'm at my minute, so I'm going to try and wrap this very briefly, these following slides. So just generally in closing, what I shared today are the preliminary set of indicators that, again, it's just a snapshot of ocean health for California. OPC is currently partnering the West Coast Ocean Alliance and Ocean Science Trust in a 2-year effort that will result in, similarly, an interactive public-facing data portal in 2025 Coast and Ocean Report Card that will publicly communicate the status, the trends of ocean and coastal health. We are also currently recruiting, it's active right now, an Environmental Justice Advisory Board for California's coast and ocean to advise on indicators and the impacts faced by individual communities, people, that of course does not replace our formal consultation and partnership with California tribes throughout the state. Next slide and last slide. Is that simultaneously, OPC is also responsible for advancing the state's 30 by 30 goals for coastal waters. That is to conserve 30% of the state's land and waters by 2030. This is a key strategy to address the twin threats of climate change and biodiversity loss, which I'm very pleased to have Madeline join me right after to discuss the 30 by 30 efforts that are taking place on land and inshore. This OPC strategy to meet California's 30 by 30 goals falls under these general 4 categories I'm happy to discuss in further detail following this panel. And with that, thank you, and I'll turn to Madeline.
Great. Thanks, Kaitlyn.